Hi everyone. Today we are going to solve it for problem number 329, longest increasing path in a matrix. So let's start with the problem statement. So given a m into n integer matrix, we need to return the length of the longest increasing path in matrix. From which cell we can either move in four directions, left, right, up or down. You may not move diagonally or move outside the boundary. Wrap around is not allowed. Okay. For example, let's say like I am currently at this cell, then I can go into the left direction, into the right direction, and I can also go in the downward direction. But I can't go in upward direction, and also I can't go in diagonal wise fashion. Something like this. This is not allowed, and this one is not allowed. Okay. So from any particular cell, we are just allowed to go upward, downward, left, and right if it is possible to visit there. If it is out of boundary, then we are not allowed to visit there. Hope you understand the problem statement. So here, let's say like we started from this cell, okay? Then from this cell, can we go to this next cell? No, we can't go because we need to find the length of the longest increasing path. So the next cell, let's say like I am trying the possibility for the right hand side cell. So here its value is 9. That is equals to the current cell value. So this we can't go. Definitely like we can't go downward because its value is also smaller than the current value. We can't go upward and we can't go to the left direction because this is out of bound. Okay. So if we choose this one as a my starting point, the length I would have one. Definitely for this 9 also I will get the length as a 1. But let's say like I started with 4. Okay. Then from 4 I can go in the downward direction or in the left direction. Let's say like I chose to go in the left direction. Okay. Okay. I cover these two paths from 4 to 9. And from 9, can I go anywhere? This 9 we can't go. This 6 we can't go. We can't go upward. And we can't go the backward one because from there only like we started. So if we choose this path, we would have this length 4 9. So let's say that instead of choosing this one, we decided to go this way, downward one. So we have 4 and 8. From it, can we go any places? No, because the right is not allowed. The downward you can't go because its current value is 8 and that the next cell value is 1 that is smaller than the current one. Similar case applies to the leftward direction also. Okay. So for both the possibilities starting with 4 either in the left direction or in the downward direction you would have length 2. Okay. Let's say like you started with 6 and I started to see like what would be the maximum length possible if I start with 6 or longest increasing path length possible. So from 6 can I go to 8? Yes, it is allowed. From 8 can I go anywhere? No, it is not allowed because you can go only in 4 direction. Okay, and upward is smaller, downward is smaller. You can't go to the left one and you can't go to the right one. So if I start from 6 and decided to go in the right hand direction, then I would just have 6 and 8. Okay, let's say like I started looking for the another possibility. From 6 can I go to the left direction? No, you can't because the left cell value is 6, that is equals to the current cell value, so you are not allowed to go there. So from 6 can I go upward? Yes, you can go there because it has a value 9 that is greater than the current cell value, so it is also allowed. Okay, so we have done the processing of this one, so we are just focusing on this one. From 9 can I go any places? This left direction you can't go, right direction you can't go, upward you can't go. So from 6 also if you start you would have two possibility only, that is 6 and 6 to 8 and 6 to 9. Okay, and for both the length is 2 only. So let's now come to the final one. So let's say like we chosen this one as the starting point. So from one, can we go downward? We can't go. Can we go right? We can't go because in the right cell the value is one that is equals to the current cell value, and we are interested in finding the increasing path. So definitely the next cell value on which I should go from my current cell would have value that must be greater than the current cell value. So from this one, can I go in the left direction? Yes, you can go. From this two, can I go in the downward direction? No, you can't. Can I go into the left direction? No, you can't. Can you go into the right direction? No, you can't because you just started from that point only. So you should mark that one as a visited one. I can go upward. Similar applies to 9. From 9, can I go anywhere? No, you are not allowed to go into the right hand direction, left hand direction, upward direction. Okay. So the max length you could have if you start from 1, this is 1, 2, 6, and 9. And this is output also. Hope you understand the problem statement. So there could be a case like we have multiple answers, and in that one in among we could have multiple answers, and whatever is the maximum length we could have, that should be the output, because if we have 4 as the starting point, we could achieve a length of 2, but if I start with 1, then I could achieve a length of 4. So the max is 4, so I'm just going to return 4 as the output, because we need to return the length of the longest increasing path in matrix. Hope you understand the following statement. Let's try to come up with some approach to solve this problem. So let me just quickly copy paste this test case. Here I have just taken for reference purpose. So we have 9, 9, 4, 6, 6, 8, and 2, 1, 1. Okay. Now here if you see, like, we have to find the path. Okay. We need to find the path. Okay. So for that one, which algorithm we should choose? Like, we have two standard algorithm to traverse the graph, either PFS or DFS. And since we are interested in finding the path, okay, so from any particular cell, what other cells can I go, and from there I will just start going to check whether the next cell is possible to visit or not. If it is possible, just go there. So if you see here, like, we are going depth wise traversal, so we should focus on DFS. Okay. So if we have to perform the level wise traversal, then definitely like PFS is the right choice, but here we should stick to the DFS algorithm. So in standard DFS algorithm, like what we used to have. So from any particular cell, like we know, like we can go up to 4 path. Okay. So let's say like I am at currently index 0, 0, then I know like I can go into 4 directions. Okay. So I'm just talking about the standard DFS that we understand, and we'll just tweak the standard DFS to solve this problem. So from any particular cell, like we have these 4 possibilities. Let's say like it is allowed to move only in 4 directions. So we could have these 4 possibilities, and after that, like whenever we are checking, like, can I go to this cell? Okay, at that place we used to check whether this cell is within the range or not. Okay, maybe it could be a case like we are at the starting of the matrix. Okay, starting cell, definitely we can't go upward. Okay, but if you are at mid, something like this, then I can go upward, downward, left, right, every places. Okay, so while checking for the next possible cell, can I visit there, then you just need to check like whether it is possible. And for checking whether it is possible or not, we check two constraints: is cell within the range, or within the matrix range, within the matrix range. And second constraint that we would have, the next cell value must be greater than the current cell value, must be greater than current cell value. Then only like these are the two constraints we could have, then only like we'll find the right path. Okay. So yeah, like we understand the problem, and understand the approach also. So we'll just implement the standard TFS, considering the constraints that we have here, that we just discussed, these two constraints. Okay, and yeah, that would be our final approach to solve this problem. So let's discuss about the time and space complexity. So the time complexity, if we observe it clearly, like what we are doing from any particular cell, let's say like let's stick to the 994668211. So if you look carefully from any particular cell, what we are doing, we are trying to check all the possibilities. Can I go to the next cell? If it is possible to go to the next cell, we are just incrementing our count. So this count simply represents the path that is possible, or the length of the path that is possible. Let's say like from this 9 I can go to this 9, then the length of the path would be 2. Okay, so it could be a case like, considering the worst case scenario, it could be a case like we, from if we start from this cell, we can visit all the matrices. Okay, it could be a case. For example, let's say like I have written my matrices in such a way: 10 11, 9 10 11, 12, 13, 14, 15, 16, 17. So if I start with a 9, then definitely I can go to this here, and this path, let's say like I have chosen. Okay, this is one of the path. If I start from 9, 10, 11, 12, 13, 14, 15, 16, 17, if I choose this path, it is also possible. So in worst case scenario, we could see like we need to traverse the entire matrix. Okay, so to traverse the entire matrix, we know its size, so it would be of order of n into m, and we need to perform this operation for each of the possible cells that is present here. Okay, so I will again start with 10, because maybe like 9 is not providing us optimal answer. So we should start with 10. And in worst case scenario, from 10 also you could have a case where you are able to visit all the matrices. Okay. So overall time complexity would be, this is the time complexity to traverse matrix. And again, like we have total number of n into m cells, so the total time complexity, if we do it in knife fashion, it would be n into m. Okay, so this is just total number of cells from where we should start performing or traversing the matrix, and this is the time complexity to traverse the matrix using the standard DFS. Okay, now can we do the optimization here? So if you see, the time complexity would be this one, and the space complexity would be like, let's say like I am storing some array where I am just marking, or if we consider the simplest scenario here where we are having this logic, then we don't require any extra space to solve this. Okay, so can we optimize it with respect to the time and the space complexity? Okay, so let's try to see the area of improvement. So currently our time complexity is order of n square m square, that we understand from where this uh, n square m square is coming. So let's try to optimize the time complexity further. Okay, because this is the only area of improvement. So even if we have to use some extra spaces, then we should use that one. But yeah, let's try to focus on optimizing the time complexity. Okay, so if you observe carefully, then what is happening currently? Okay, let's say like we have this test case 994668211. Okay, so from any particular cell, let's say like I'm starting and I'm doing the processing. Okay, I visit there, something like this. I'm just randomly drawing, I visited there, I visited there, something like this. Okay, and we are just calculating and having some variable where we are just updating it accordingly if we find the latest path that is having a higher number of counts or higher number of nodes in between. Okay, but if you observe carefully, like when again we start processing for this node, then again like I will follow the same path, because from here also if I start the DFS, we will follow the same path. Then why not we should store the information that we have already processed? Because if you start from here, then what in DFS we are doing, we are just making a recursive call. Okay, so here if I started from 0 0, I, and it is making call to 0 1. Okay, and this is making call, let's say, to 1 1. It is making call to 2 1 and 2 2, something like this. Okay, and after that only like we would have result for this one, let's say 4. Okay, but let's say like we have to perform this operation for all the cells. for this one we have performed, for this one also we'll try to perform. But if you see here, we have already processed all the path, okay, or the DFS for this cell also, while we are processing for this cell 00. Okay, so instead of just returning the result, what we can do, we can also start storing the intermediate result. Okay, so for each of the cell, because we know like if I start from DFS for this index 01, then it would also follow the same path, the path that I have followed or that our algorithm has followed when it has started from 00. Okay, from 00 it comes to this 01 and follow the same path that it would also follow when it will start from 01. So instead of just returning the result, we should store the intermediate result. Then in that way, like what we could have, like we can say like if the call came for this one, like, or when we start processing for this one, then we already know its information is already stored in some places. We'll start utilizing that value instead of making the actual calls and doing the actual processing. So simple caching we can say like we are implementing here, and this standard technique is called memoization technique. So instead of processing each of the time, what we can do, we can store the result and start utilizing that result. So in that way, what we could have, if I started from this cell, I done the processing. Let's take the real example 994 668 and 211. And let's say like I'm creating a 2D matrix where I would store the result of each of the possible cells. Okay, let's say like I started from this 9. So by default, all are initialized to 0. Okay, and if it is not 0, then simply means like we have processed that cell, we could start utilizing that result. And if it is 0, then we need to do the processing and calculate the result, and then only will update it. Okay, so from this cell, like I will start, and from this cell, can I go somewhere? So definitely we see here like all are 0 initially. So yeah, go ahead and start doing the actual processing, and after that we can store the value for this one, so that the next time, if any call is coming for this particular index, we'll start utilizing the result. Okay. So for this 9, can I go somewhere? No, definitely we can't go this one, or any other places. So its value would be 1. Okay. For this 9, if we say here like, yeah, okay, for this 9, like when we are checking, definitely it's not possible to visit any of the cell. So that's why like we have not made any DFS call. If we have made the DFS call, then we should start storing the state for that DFS call also. Okay, so from this cell, can I go anywhere? Like I can't go here, and I can't go here, I can't go here. So for this one also the value is 1. For this cell, can I go anywhere? Like here, from this 4 I can go to 9. Okay, and from this one, like we already know its state. Okay, it's 1. We already know that one. Okay, so 1 for this one, and 1 if we are utilizing, and uh, this value, so 1 plus 1 2. Okay, and from this 4, like we can go to one more places, that is 8. Okay, so if you see like for 8, like we have not done any processing, but we can go to these places. Okay, and from these places, can I go anywhere? Can I go to 6 or 1 or any other places? No. So for this 8, the call would be 1. Okay, and it will traverse back or reverse back. Since the recursive call from 4 to 8 has completed, it is done with the processing. So call returned back to 4, and for 4, like 1 for this 4, and 1 for this intermediate one, 8 1. So it's 2. So we see like for 4 we have two paths. One is 4 9 and one is 4 8, and the max of them is for both like 2 and 2, and max of them is also 2. So we'll just keep it as 2. And let's say like if I have find something like this 9. Okay, so from 4, if you see like we have first path 4 9. Okay, and the next path, if we started going downward, we see like 4 8 and 9. Okay, then in that case, the max length path is 3. So for this 4, we can update it to 3. Okay, but here our original input is 1. Okay, so we'll just keep it 2. Okay, so next I will start from this 6. From 6, can I go any places? We can go upward. Okay, it is possible. And for upward, we already know the result. Okay, so 1 for this 6, and for 9 we already have stored the result, so it would become 2. Okay, and for 6, can I go downward? Can I go left? Can I go right? No. So this is the final result for this 6. So let's say like I started processing for this 6. Okay, From this 6, can I go any other places? I can go to 9 or 8. Okay, let's take the path of 9. Okay, so if I go to 9, for 9 we already know the result is 1. So it would become 2. From 6, I can go to 8 also. So the path would be 2 only, because for 8, 1 and 1 for this 6. And max of this 2 and 2 is 2 only. Okay, so we just keep it 2. Again, we'll start from this one. For this 2, can I go to some places? Yeah, you can go to 6. For 6, we already have stored the result for 2, and 1 for this one, 2, 1 for this 2, and this 2 is from 6, so it would become 3. Okay, and for 1, so even for 2, like you can't go to any other places, only this one is the only path. From 1, can I go to one any other places? You can go to 2. Okay, so it would value would become 4. And from 1, can I go to 6? Yes, you can go to 6. And for 6, we already know the value is 2, so 4 comma 3, that is 2 plus 1, so the max is 4, so we'll just keep it as 4. And from this one, can I go to any places? Yes, you can go to 8. Okay, so for 8 we already know 1, and we'll just utilize this result, so it would become 2. So at the end, if you see, like we have all states information stored here, and the max one is 4, so that's why the max length or the output is 4. So let's try to quickly solve it. So if we apply this memoization technique, then time complexity would reduce to order of n into m, and space complexity would become order of n into m. Okay, so we have reduced the time complexity from n square m square to order of n, and we have increased the space complexity from order of 1 to order of n into m. So considering the today case scenario, definitely like we don't have any strict limitation on space, we can assume like we have infinite space, but we have very limited time. So we focus or say like this one is the optimal approach. Now we'll just go ahead and implement this solution. I'm just initializing and an m so that we can reutilize it whenever it is possible. This is the side of the matrix that we are having. So we discussed like we'll implement the optimized solution, and let's say like I am naming my cache as widget. Okay, it would be of nature integer type. That I will store the value 1, 2, or whatever is the length if we start processing from a particular cell. Okay, so this is the same. Let's try to iterate the matrix and start processing for each of the possible cells. Okay, so we just need to return the max len, okay, at any point of time. So what I will do, from each possible cell, I will just calculate the length, and whatever the maximum length is possible, I will just store it, because at the end we just need to return the length of the longest increasing path matrix. Okay, and from here I will just make a TFS count. Okay, so here I should pass the required attributes IJ and paste it. That's all. Let's initialize the variable that I have just introduced with 0. Makes sense? And at the end we can just return this max name. Okay, let's try to implement the method that we have introduced, that is this TFS. Okay, so this is the signature of this TFS method. It is taking one 2D matrix, and after that the coordinates, and after that one cache, and we are naming this cache as wasted. Okay, if in our cache the elements are present, it simply means like we have done the processing for this particular index, so we can utilize that value. Okay, so I'm just doing that thing. Otherwise, like we need to go ahead and start doing the processing. I'm just creating an array for all the possible directions. Perfect. Let's try to iterate. through all possible directions. Whenever like we are going to explore the next field, we just need to make sure the next field is valid or not. So for that one, I'm just making one call. If it is possible to visit there, then also like from any particular field, like you could have multiple paths. Okay, so one path could be using the left one. So let's say like you chosen to go in the left direction, that is 9. And from there, like if it is possible to visit the other path, visit there. Otherwise, we have one possibility. From 4, you can go to the download also and start from this path 4, 8, and after that, just see whether it is possible to visit any other path or not. Okay, so at least 4 paths would be introduced from any particular cell. Okay, so we should take the maximum of that path, and this is just a recursive call that I am making. Whatever is the maximum path on this one, we should utilize that one. Okay, let's initialize this value with 0. Okay, and yeah, while returning we should choose the maximum of this one. And since we are optimizing by introducing the memoization technique, now let's implement another method that we have introduced, that is this is valid. Okay, let's write down its signature. It is taking one grid, some coordinate value x and y, and after that we have the current element from a particular cell from where we are started to check for the next possible cell. Let's calculate. I'm just calculating in NM, and after that we should just have the standard check for the boundary. So it should be greater than equals to 0, it should be less than n, y should be greater than equals to 0, and y should be less than n. And current grid value, that is x and y, should be or must be greater than the current element. If it is satisfying, then it's a valid cell. We are in the range. Go and try for all the possible paths we could have. Take the max of that one and store that information. So this plus one is just for considering that current cell. So let's see, is there any compilation issue? I see like we have some compilation issue. Okay, let's rename this matrix itself as string. So now for the given test case, it is working. Let's start. Let's check it for the another test cases to ensure its correctness. If it pass, then I will try to submit it and see how it is going. Okay, so somewhere I have done some mistake. So the format through which we are providing the input is not correct. Now it is correct, so it should work. Okay, it is working for all these three inputs. So let's submit it. Okay, so it has accepted. So although like here we see like we can do more optimization because here it has taken 12 milliseconds and that is faster than only 30% of the Java Online solutions. But this is one of the approaches through which you can solve this problem, and in this approach we have just utilized the standard DFS technique to traverse the graph. So yeah, that's it.